So this lecture is on maximum likelihood estimation and maximum a posteriori, and it's all about like where do our loss functions come from? How do we derive good loss functions for our problems? How do we figure out what loss functions are right to use? And there's going to be a little bit of a twist partway through, so do stay tuned. And there's also going to be some pretty obnoxious maths, but it's mostly horrible, chaotic notation rather than anything too difficult or strenuous. So we're going to use an example problem for this presentation, and this is noisy multivariate linear regression. So there's a linear system that is parameterized by some true weights W star. So y of W star of x is W star dot x. You're like packaging a bunch of this big weighted sum into a vector dot product. However, there's some noise in our system. There's some aleatoric uncertainty in our output examples, and we've seen this before as like a little epsilon term. I'm going to be running it slightly differently for this lecture. Instead, we're saying that it is that each output example is drawn from a normal distribution with mean of this like W star dot x and variance, this like true variance, which is also unknown, just like sigma, W star, and that is sigma. And I'm packaging that all together into one giant multi-dimensional normal distribution. So it's like a Gaussian curve in many dimensions around this like x times w. So it's like we evaluate all our model, the true model on all our training examples to get this like mean, and then we put some noise around it. And the noise is something called the covariance matrix, where like element ij is the variance of I with respect to j, pretty much. And because we're using a multiple of the identity matrix, we're basically just saying it is a ton of independent normal distributions around W star dot x example, basically, just all packaged together into a big normal distribution for convenience. So in order to evaluate our model and find like our own W that best matches W star, we want to use local search, like gradient descent for this. We're going to need a loss function to like say how bad our model is. And here's a couple of the possible functions we could use. Option number one is mean squared error loss. So you evaluate the model at each input example. That's the like xi dot w, and you take the difference from the corresponding output example, and you take the absolute value. But instead of absolute value, we're going to use square because it makes the differentiation and the other calculations easier. And then you sum them up and you divide by the number of examples. It's like, on average, how far off is your model? And we're ignoring the 1 over n factor out the front because we're optimizing it. It's going to get lost. It doesn't matter. The other option is dot product loss. So if you do this x times w vector matrix multiplication, you're going to get all your outputs, and you have all the like real outputs. And by taking the dot product between those two vectors that contain a bunch of outputs, you can measure how similar they are. So like vectors that point in the same direction are going to have high dot products. Vectors that point in the opposite direction are going to have negative dot products. If they're completely disconnected, they're pointing in like perpendicular, they're going to have a 0 dot product. And so we can sort of measure how similar our outputs are to the real outputs. We do have to divide by the magnitude of xw because the dot product also scales proportionally to that and the magnitude of y, but we ignore it because of optimization. And we don't want to like have that influence our loss. Otherwise, we would instead train the model to have, I think, some different stuff. It would mess it up. And obviously, we're using a negative because we want to minimize this. So these are two very different ways of looking at a loss function, of like making a loss function, and these are just a couple of the many options. There's also a bunch of different ways you could do each of these, and like how do we decide which is right for us, and how do we evaluate different loss functions. We can't test all of them because there's too many, and training them all would take too long. And so how do we like derive a quote unquote most natural loss function from our problem specification? So this is where maximum likelihood estimation comes in. We make a little important assumption about our training examples. We like assume they aren't outliers. If we've got a large training set, this is probably true, because if we sample like 100 different, or like a ton of different inputs and outputs, you're very unlikely to get a set of like a training set that is all outliers. And so for our model to be good, common stuff should be common and rare stuff should be rare. If it's like saying this crazy weird outlier should be occurring 90% of the time, then your model's probably very, very wrong. So that's a little too big. We can find W by maximizing the probability that our model generates Y. So if we have a similar normal distribution around XW instead of XW star, and we maximize the probability that our Y is drawn from that, then we can find a really good W. So we can use this kind of idea of like maximizing the probability that our parameters generated the training data, and that idea kind of works for any problem, and we can like use that to derive a very good natural loss function for whatever situation we end up in. And so for that we need something called a likelihood function. It maps every parameterization onto the probability that the parameterization generated that data. And so in our example, we're using this same technique of let's package a bunch of independent normal distributions into a big multidimensional one, to say what is the likelihood that the likelihood of our parameter is the probability that this high dimensional cloud of Gaussian probability generates this generates these output examples. We don't know the true variance like sigma from before, so we're using our own like sigma star, which our model is if we like incorporate it into gradient descent. If we do gradient descent with it as well, like we take its find its partial derivative with respect to it, and we update it every step, it will then learn to match the real sigma. So what we also get from this technique is when we make future predictions, our future predictions are going to be noisy, but they're going to have the same noise as the inputs, and so it's going to give nice realistic examples, which is very fun. So yeah, this is a continuous distribution, so technically what we're looking at here is a probability mass function, but due to like optimization, it doesn't actually make a difference. They're still going to have the same maximum. But this is ridiculous. What am I doing? I'm asking you to maximize a high dimensional Gaussian. The maths for that is going to be horrible. Would you even be able to compute that in like a reasonable amount of time? And yeah, don't worry. It's actually, don't forget, it's just a ton of independent Gaussians packed into a vector for shorthand convenience. And with the magic of logarithms, which again, monotonically increasing, so they're kind of ignored by optimization, we can avoid like the horrible exponentials, the like e's in the normal distribution function, and we can get rid of that big product because again we're multiplying a bunch of independent Gaussians together effectively, and turn that into a sum instead. So yeah, lots of scary looking math on the next slide, but bear with me. A lot of it is just sort of constant factors and annoyances. So yeah, so we start by in the first line unpacking our crazy high dimensional sort of shorthand into this, you know, product of independent normal Gaussians, and then we like expand the Gaussian definition and we pull out the constant factor. And what we're saying is that the logarithm of this is so we take the logarithm and then we pull out some extra constant factors, and what we have here is on the right hand side, on the bottom right, there's this sum of squared errors. That's right. Here's the twist. It's a pretty boring twist, but the L2 loss is equivalent to maximizing the log likelihood. Or it's equivalent to maximizing the likelihood. By doing this maximum likelihood estimation technique, we end up with like deriving L2 loss. That's where it comes from. So it's not necessarily true if the aleatoric uncertainty doesn't have like certain properties, then this isn't, the maximum likelihood wouldn't necessarily be L2 loss. So if they're not independent, you can't product everything together. And so when you take the log, you're not going to get the sum. If this aleatoric uncertainty isn't Gaussian, you're not gonna have that e to the minus x minus mean squared term, and so you're not gonna get L2 loss. And if the variances are all different, then that's gonna mess you up as well, because you're not gonna be able to pull up out the constant factors. Couple things that make this quite common. One, this is equivalent to having a epsilon, term that's like normally distributed around 0 and adding that on. And so in situations where like the problem is specified like that, this, the maximum likelihood is also L2 loss. And also there's this idea called the central limit theorem, where if you sum up a bunch of different probability distributions, if you add enough together, you're eventually going to get like a Gaussian. And so if there are like a ton of factors that go together to make like the noise of your in your output, to like make your aleatoric uncertainty overall, even if they're all very different, differently distributed, they're all going to combine into one big sort of Gaussian or Gaussian-ish. But what? Like, no, that's still like stupid. The assumptions on this rely on having a slightly ridiculous amount of training data, and it's super vulnerable to epistemic uncertainty. Like, this is kind of the definition of overfitting. Get the best parameters for the training example, for like the training data without any and if the training data is like super wacky or super outliery, then you're gonna have terrible you're gonna have terrible model performance, because because your parameters are going to massively overfit. So instead what we want to say that we don't want our parameters to go crazy, and so we want to incorporate some like pre-existing assumptions we have about our parameters into this into our maths. Like we want to like incorporate our pre-existing understanding of what our parameters kind of should be, and so if the training data pulls them over into like crazy land, then it's like Texing land but crazy. Then your pre-existing assumptions are going to kind of work against that and stop you from overfitting too hard. And the idea of incorporating your prior understanding of distributions is exactly what conditional probability and Bayesian probability theory is all about. So we're going to spend some time talking about Bayesian probability and conditional probability. The idea is that conditional probability is a like probability. It's a probability function. It's like, what's the probability of this value, but it's parameterized by some other events or random variables or distributions, whatever. And specifically, instead of using like a semicolon like you would normally use for like extra parameterization, use a bar instead. And this bar symbol symbolizes that you've got this fraction relationship here where the probability of A given the other things it's parameterized by, the other events you use to build up this function, is the probability is this probability of all of the events being satisfied divided by the probability that B given the rest of the events. There's this like relationship here, which I'm sure you guys have seen the Venn diagram set up like 100 times, where it's like the area of the intersection divided by the area of the right hand side. So the bar, it just represents like, oh my god, the probability function is dependent or like parameterized by these other events with this special relationship. It's very small at the bottom, so let me restore that to its reasonable size. But if you swap the math cal p's, the like fancy p's for, you know, big p's and like little p's, you can there's an equivalent property for, as an analogous property for random variables and probability distributions. So using this this idea of conditional probability, we can derive something called Bayes' rule, which is how it's all about updating your understanding of uncertainties with new information. And this lets us incorporate our quote-unquote prior understanding of random variables into our calculation. So this is what we're going to use to get to avoid this overfitting problem. So the P of A and P of B here are called priors. They're like, here's what we thought we knew. Like, before we receive this information, here's the probability of event A, and here's the probability of event B. P of B given A is called the likelihood. It's like, what's the probability that the outcome satisfies event B, given that it also satisfies event A. And the posterior, like but, is this P of A given B term on the left side. And so that's what like all these different parts are called, just so you know the names when they turn up in textbooks and things. So we're flipping the problem a little bit to, instead of finding the W that is most likely to generate Y, we find the probability of that our parameters are W, given that we've received this input and output data. And there's a bit of a silly example for how you can use Bayes' rule to like update your information, your uncertainty. So if you're walking down the street and you walk past somebody, the probability their program is like P of A. We're gonna say it's P of A, and you say hi to them because you're a polite person, and they like tip their fedora at you and they say like "milady" or whatever, and that's changed, right? The probability their programmer has like changed somewhat. How much has it changed given this new information? Well, if there are a lot of programmers are neckbeards, as in the probability that someone is a neckbeard, given that they're a programmer, is very high, then this new probability is going to be very high. But if a lot of people are neckbeards, so if the probability that someone's a neckbeard is very high out anyway, then this is going to have a sort of counter effect. It's going to decrease this new updated probability. And so we multiply our prior by this like proportion, by this P of B given A, and we divide by this counter effect, and so we can see how much our information has changed, how much our probabilities have changed given this new information. So let's make some assumptions. It's time to make these assumptions about W we keep talking about. So first of all, if you've got a large number of input variables, a bunch of like things you're measuring, most of them are going to be irrelevant. Like a good chunk of them are going to be irrelevant. So we're going to assume that most of our parameters are distributed around 0, and they're going to have the same variance sigma naught, and this is a hyperparameter So it's not something we learn with gradient descent, unlike sigma w, which we do learn with gradient descent. And it like there's a bunch of different ways you can figure out what the right value for this should be. There's like leave one out validation, but there's also Bayesian techniques. But this is unfortunately beyond our scope, and we're packing all this together into one big distribution, like high dimensional distribution that you then is our distribution over parameters. And if these assumptions aren't great, then the training data is gonna counteract that a bit. And if our training data is full of outliers, then our assumptions are going to counteract that to get a bit, and we end up with this like pulling one way, pulling the other way effect, and it sort of cancels out. In this bad situation, in the ideal situation, we don't have horrible outlier field trailing data, and we have reasonable assumptions, and everything works great. But if there's an error in one, then the other is going to go pull things back to being correct. So let's do it. Let's calculate the maximum posterior. Using Bayes' rule, we see that the probability that we generated the probability that we get our parameters, given that they output y, is the probability that y is output by our parameters times the probability of our parameters occurring, divided by the probability of our outputs occurring. The problem with that is the probability of our outputs occurring depends on sigma w star and sigma, which we don't know. So we're stuck, right? We're not stuck, don't worry, because this is like a factor. It doesn't depend on w. So if we're doing argmax or argmin or whatever if we're doing optimization, we can ignore it. So we do not need to stress about it. So the maximum, the w that maximizes the probability that like these are the parameters, the correct parameters, given that we've seen this data, is the maximum of the log likelihood plus the log of the probability of our parameters. So let's go have a look at what the log of our probability of our parameters is. Again, we start by unpacking our crazy multidimensional normal distribution into this product, because again, it's just a bunch of independent probability distributions next to each other. And then we expand the normal distribution formula, pull out a bunch of constant factors, and these are for real constant factors because they depend on sigma naught, which is a hyperparameter. So it like, for all intents and purposes, it's a constant. And we get this like sum of the squares of the parameters. We get like the norm squared of our parameter vector. And yeah, it's the same twist again. Twist 2, I know, there's another twist that's just as boring. Like, maximum a posteriori is the same as, it's equivalent to L2 loss and like regularization. This like standard stuff that you learn in AI1 that you just kind of get handed to naturally falls out if you make some pretty reasonable assumptions and perform this maximum a posteriori process. But like, so why do we care? Why does this matter? If we just end up with L2 loss and regularization that we already know about, what's the point of going through all that maths? And yeah, in practice, we can just kind of use L2 loss and regularization for everything. But if the aleatoric uncertainty isn't Gaussian, then the maximum likelihood isn't going to be L2 loss. And if the prior distribution over parameters isn't Gaussian, then your regularization term might not end up being the norm squared. But for any problem, like even like really weird alien problems where you can't figure out what would be a good loss function, you can do this. You can have a look at the probability. You can take like a Bayesian perspective, and you can derive a really good loss function by finding the posterior. Doing maximum a posteriori, it like lets you derive a great loss function that has like a regularization term of some kind that works well in this context, in whatever context you're in, to avoid overfitting. But also that like learning why these formulas are the way they are is super like it it helps you like understand everything and apply things better. It just gives you a better, deeper, like a better and deeper appreciation for uh, AI stuff, for like regression and for whatever you're working with. So thanks for your attention. I've kind of sped through this a little bit, and then on the next slide, I've got the full horrible formulae for gradient descent, including all the constants and uh, like sigma w, and the like probability distributions and stuff. So I can like talk through those if you want. Um, there, more importantly though, are there any questions? Is there anything where you're like, what the hell, Hux, what are you doing? um, is there anything you need me to go back and elaborate more on? Right, okay. So the likelihood function is at the highest possible level a function that takes in some parameters and says what is the probability that they generated this data. Um, so if you had, let's say, like if you had, let's say, like 3 neural networks or whatever and some data, and you were like, which of you guys did this crime? You know, you did like a police lineup. You can you can set, it's like, what's the probability that these parameters committed the crime effectively. It's like I yes. So it's trying to find the parameters that are the most suspicious model. Yeah. So no. So MAP is starts with your like initial suspicions. So maximum likelihood is which of you is the most likely to have done it given the like crime scene evidence, whereas MAP is like, okay, but this guy has a criminal record already, or this guy comes from like a rough upbringing, or whatever, some existing assumptions about the parameters, whereas MLE is just looking at evidence. Whereas if someone's sort of more suspicious, just kind of without looking at the evidence, then that's like PW basically. Yeah, that's the P of W is quantifying how expected those weights are. Yes, and that's the source of this external information that we're incorporating into our AI. Yeah. Yeah. Yes. It that's exactly that's true. What differs is that you're multiplying by P of W. Well, technically, you're adding log of P of W. But the reason that we say we're going to multiply by P of W, or like add log of P of W, is because of this Bayes rule idea of updating. Yes, it depends on W star, which one we don't know. Yes, and W star is constant. These are like the secret true values that we're trying to get W to match. That's the same with sigma and sigma W. We're trying to get sigma W to match sigma. Are there any further questions?